To most people at NASA, 3 Atlas was just another strange rock drifting through our neighborhood. An interstellar visitor, yes, but still an object that obeyed the same old rules of gravity and chemistry we've been studying for a century. When the James Webb Space Telescope was scheduled to spend a full 72 hours locked onto it, many expected nothing more than a few beautiful spectra, a couple of conference papers, and maybe a headline or two. But from the very first batch of data, it became clear that this was not going to be another routine observation. The red flags started appearing almost immediately. The observation run was designed to be exhaustive. Webb's near-infrared spectrograph would dissect the light coming from 3I Atlas, teasing out the fingerprints of the molecules on and around it. The mid-infrared instrument would track its heat, revealing how energy moved across its surface. And the imaging systems would give us a high-resolution look at any structures, jets, or dust clouds surrounding the object. On paper, it was a perfect chance to autopsy an interstellar visitor with the best instruments humanity has ever launched into space. In practice, it felt less like an autopsy and more like listening to a heartbeat you didn't expect to hear. The first anomaly wasn't dramatic, it was subtle, almost easy to miss. Analysts noticed that the initial spectra were wrong. Not noisy, not broken, just off in a way that didn't match any of our templates. The usual suspects, simple gases, common ices, familiar organic compounds, weren't lining up with the absorption lines appearing on their screens. Instead of the clean, predictable patterns you see in comets and asteroids, 3I Atlas was showing a dense forest of lines clustered in regions that, frankly, shouldn't be that busy. For a rock that had supposedly spent eons drifting between stars, it looked chemically crowded. At first, the teams did what scientists always do. They blamed the instruments. Maybe there was a calibration drift. Maybe some solar flare had interfered with the detectors. Maybe the data pipeline had a hidden bug. For hours, people reran simulations, checked reference stars, and cross-compared the readings with other targets observed the same night. Everything came back clean. Webb was working exactly as designed. The problem wasn't the telescope. The problem was the object. When they began to break down the spectral features in detail, the strangeness escalated. The signatures weren't dominated by simple molecules like methane, carbon monoxide, or water vapor. Instead, they were seeing evidence of long carbon chains, complex ring structures, and heteroatoms woven into elaborate frameworks. To anyone outside the field, those terms sound abstract. But to chemists, they mean one thing: complexity. The kind of complexity you usually associate with something that had a reason to exist, not with random reactions in frozen dust. Then came the thermal data. While the spectrograph teams were still arguing over molecular models, the mid-infrared instrument quietly delivered its own warning. 3I Atlas wasn't heating up like a normal object would. It wasn't just a lump of rock passively absorbing sunlight and re-emitting it as heat. Instead, its surface was dotted with localized regions that were significantly warmer than their surroundings, spots that brightened and faded in patterns that refused to fit any simple explanation. When those thermal maps were overlaid onto the preliminary images, the result made more than one researcher lean back in their chair in silence. You'd expect temperature variations on a rotating object, of course. Day and night sides, shadows cast by irregular shapes, maybe even thermal inertia in different materials. But that's not what they were seeing. Some regions stayed warm even when they rotated into darkness. Others pulsed in brightness on timescales of minutes, not hours. Even more unsettling, a few of those hotspots seemed to talk to each other, brightening in one location, followed by a rise in another, as if heat were moving along invisible pathways carved across the surface. By this point, the default explanations were running out. You can invoke exotic geology only so many times before the patterns start to sound less like geology and more like behavior. Still, no one was willing to say that out loud. Instead, they buried their unease in technical language, describing the anomalies as non-equilibrium thermal regimes and unmodeled energy redistribution. Behind those careful terms, though, was a simple, unnerving thought: this object is doing something. As the 72-hour observation window continued, the datasets piled up, and the something became harder to ignore. The spectral signatures were not static. The relative intensities of certain lines shifted over time, as if the concentrations of specific molecules were changing in a coordinated way. The same patches of the surface that glowed with excess heat were also where the chemical signatures seemed to evolve the fastest. Whatever processes were happening on or inside 3I Atlas, they weren't frozen relics of its past. They were active, ongoing, and responsive. That responsiveness triggered the first real alarm. In one sequence, analysts watched as a region on the surface cooled slightly, only for an adjacent region to warm up a short time later, with the spectral fingerprints of key molecules changing in tandem. It looked eerily like a system shifting resources from one area to another, as if it were redistributing energy, moving material, or reacting to some internal signal. Suddenly, the idea of just a rock felt hopelessly outdated. Inside conference calls and encrypted channels, the conversations grew more urgent. Nobody was claiming life yet. That word carries too much weight. But phrases like organized complexity and non-random spatial correlation began to appear more and more in internal memos. On the surface, these are dry scientific expressions. Underneath, they reveal a simple truth: the patterns didn't look accidental. Still, the scientific instinct for caution is strong. Every new anomaly was followed by an equal and opposite wave of skepticism. Maybe the object carried exotic ices that sublimated in weird ways. Maybe its spin axis produced unusual illumination patterns. Maybe we were seeing the result of fractures, outgassing, or buried volatiles. Each explanation worked for one piece of the puzzle and failed for the others. Every time a natural mechanism was proposed, another part of the data stubbornly refused to fit. By the end of the observation run, the mood had changed completely. What began as a spectacular opportunity to study an interstellar object had turned into a mounting list of questions that no one could comfortably answer. The chemistry was too rich. The heat patterns were too organized. The time evolution was too coordinated. You could either call it the most complex non-living system ever detected, or start entertaining a possibility most scientists spend their careers avoiding. Those first red flags from James Webb didn't prove anything on their own. But they did something far more important. They forced everyone involved to look again, more carefully, and ask a question they never expected to ask about a wandering object from deep space. If this isn't just geological, then what exactly are we looking at? From the moment the chemical data began streaming in, it was clear that James Webb wasn't just observing 3I Atlas. It was uncovering something that defied every expectation about what an interstellar object should be. If the first anomalies had raised eyebrows, the chemistry that followed raised heart rates. This wasn't random molecular noise, nor the simple organic haze we find drifting between stars. This was something far more structured, far more intentional, and far more unsettling. When scientists analyze an object in deep space, they expect a familiar pattern, a mixture of gases and simple molecules left behind by ancient stellar processes: methane, carbon monoxide, ammonia, maybe a few small organics if the object has been around long enough. They expect the chemistry to be messy, uncoordinated, and governed by probabilistic reactions that occurred over millions of years. But the first detailed breakdown of 3I Atlas immediately broke that pattern. The lines weren't just dense, they were clustered in ways that looked engineered. The most striking discovery came from the long-chain carbon compounds. These chains weren't the short, chaotic fragments you'd expect from cosmic radiation acting on ices. Instead, the carbon skeletons ranged from 20 to 40 atoms lengths associated with metabolic lipids, cellular membranes, and complex biological scaffolds. On Earth, such molecules typically arise not from random chemistry, but from the precise, regulated processes of living organisms. And the ratios were all wrong, dangerously wrong for any natural formation mechanism. In non-biological systems, you see abundance curves shaped like a decaying slope. Simple molecules dominate, and the complex ones appear rarely, almost as accidents. But 3I Atlas displayed a pattern inverted from the natural norm. The complex molecules were not rare, they were dominant. And the simpler precursors, the stepping stones of synthetic pathways, were oddly scarce. It was the chemical equivalent of finding a library filled with completed novels but no drafts, no notes, and no discarded pages. That imbalance alone would have been enough to trigger intense scrutiny, but the next finding pushed the conversation into territory many researchers were deeply uncomfortable with: chirality. Most organic molecules can exist in two mirror image forms, left-handed and right-handed. Abiotic chemistry creates both equally. Life, however, chooses a side. Earth's life forms, without exception, use left-handed amino acids and right-handed sugars. This preference, that elegant, universal bias, is one of the most powerful signatures of biology we know. So when analysts discovered that several molecular families on 3I Atlas exhibited strong chirality, the atmosphere in the data room shifted instantly. The ratio was not the clean 50/50 split of natural processes. It was heavily skewed around 85% toward one-handedness. Such an extreme lean is virtually impossible without selective synthesis. And selective synthesis implies purpose. Something was choosing molecular forms rather than accepting the random lottery of cosmic chemistry. Yet even that wasn't the most disturbing part. As the team dug deeper, they noticed something completely unprecedented. The molecular distribution was spatially organized. The same complex molecules repeatedly appeared in specific regions of the object, concentrated around the strange apertures where heat and activity were strongest. It wasn't a uniform chemical soup. It was patterned, structured, almost territorial. On Earth, this kind of distribution corresponds to tissues, organs, or specialized functional zones within a biological organism. In the oceans, hydrothermal vent communities organize chemicals around nutrient flows. Inside cells, compartments maintain distinct chemical environments for different tasks. In 3I Atlas, the parallels were disquieting. Certain molecules formed clusters around the openings, while others seemed to dominate the deeper layers inferred through spectroscopic depth modeling. It looked like a biochemical map, a layout of processes working in tandem. That alone would challenge the foundations of astrochemistry. But there was something the researchers kept returning to, something that made everyone pause before speaking. The molecules were changing. Over the course of the 72-hour observation, concentrations shifted. Some species rose, others fell. Ratios adjusted in ways that mirrored feedback loops' chemical regulation. It wasn't chaotic variation. It was controlled, seasonal, almost rhythmic. The most troubling part came when analysts noticed that shifts in chemical concentrations aligned with shifts in thermal hotspots. As certain molecules increased in abundance, local temperatures rose slightly. When the temperature fell, different molecular families appeared in their place. To an outside observer, this might seem abstract. To those studying it, it was the unmistakable signature of processes reacting to internal conditions. If it had been just one-piece complex molecules, they could have explained it away. If it had been just chirality, they could have argued for exotic prebiotic chemistry. If it had been just spatial organization, perhaps they would have invoked unusual geology. But all of them together? Complexity, selectivity, regulation, and dynamic change, this combination forced experts to confront a possibility they'd spent their careers avoiding. Not because it was scientifically impossible, but because it was existentially overwhelming. These molecules behave as though they were not merely formed, but maintained. And yet, even as unsettling as that conclusion was, it still wasn't the most confounding discovery in the chemical analysis. Because tucked between the known molecules and the complex organics lay something even more inexplicable. A set of spectral lines belonging to molecules that do not exist anywhere in our catalogs. Unknown chemistry, unknown purpose, unknown origin. The kind of chemistry you'd expect not from nature, but from something evolving according to rules we don't understand. And as the chemical signatures deepened in mystery, the thermal and structural data waiting in the next phase would push the scientific community past the line between the extraordinary and the unthinkable. Because chemicals alone don't behave like this. Systems do. Living systems. If the chemistry of 3I Atlas had shaken the scientific teams, the thermal data shattered them. This was the moment dozens of researchers across NASA, MIT, Caltech, Oxford, and STSCI stopped trying to explain the object as a geological oddity and began confronting a far more uncomfortable possibility. The heat signatures coming off this thing looked coordinated, not random, not chaotic, not the passive cooling and warming cycles of a drifting chunk of rock, but something organized, something adaptive, something behaving. James Webb's mid-infrared instrument, MIRI, isn't just a camera that sees heat. It's a precision tool capable of mapping temperature variations across an object with astonishing detail down to tens of meters. For typical comets and asteroids, the resulting maps are predictable. Warm regions follow the sunlight, shadows cool down, surface roughness introduces minor asymmetries. Everything is explainable with simple thermodynamics. But when scientists processed the first full-surface thermal map of 3I Atlas, the room went silent. The heat wasn't following the Sunday. The brightest hotspots didn't correspond to illuminated areas. Some remained warm even during complete darkness. Others pulsed, brightening and dimming in cycles so regular they bordered on mechanical. And the pulses weren't isolated, they were connected. When analysts plotted heat fluctuations over time, they discovered something impossible. A network of 183 distinct hotspots across the surface, each linked to others through synchronized thermal rhythms. In geophysics, synchronization of heat is unheard of. On Earth, even the most active volcanic systems don't coordinate temperature in patterns like this. Heat diffuses randomly, conducted and radiated without preference. But on 3I Atlas, pulses in one hotspot would consistently precede pulses in another, sometimes by minutes, sometimes by seconds, forming what looked disturbingly like pathways of energy flow. It was as if the object were routing heat the way a nervous system routes electrical signals. And that comparison isn't poetic, it's mathematical. When MIT's Dr. Robert Martinez ran correlation analyses on the temperature sequences, he found something baffling. The network displayed small world topology, a structure characteristic of neural networks, social networks, and biological systems optimized for communication. In simpler terms, the hotspots weren't isolated pockets of warmth. They were nodes in a web of interactions. Even more disturbing, the network efficiency resembled something designed to move information quickly across a large system. At this point, the conversation inside the scientific community changed. They stopped asking, "What is causing these hotspots?" and started asking, "What are they doing?" The data suggested coordinated behavior, patterns repeated, signals propagated. One cluster of hotspots would oscillate in lockstep, while another would respond with a delay that suggested dependency or response. If it had been a geological feature, every hotspot would behave independently. But here, each one seemed aware of the others. When scientists animated the 72 hours of thermal evolution, the effect was eerie, as if 3I Atlas were breathing, expanding heat in broad waves, then contracting into smaller clusters. It wasn't literal respiration, of course, but the patterns evoked the same cyclical organization. And these weren't single-layer phenomena. Different regions displayed different behaviors. Some pulsed rapidly, others slowly. Some acted as hubs, sending out waves of thermal change. Others responded like peripheral nodes following instructions. It looked like a hierarchy. It looked like control. It looked like communication. Parallel to the thermal data, researchers were analyzing the structural maps from Webb's near-infrared imaging. As expected, they saw the strange apertures, circular openings, 50 to 80 meters wide, scattered across the surface. They had been noted before, but now, with thermal data aligned, something became unmistakable. The most active hotspots surrounded those apertures. They weren't cracks. They weren't geysers. They were focal points, centers where energy, chemistry, and heat converged. On Earth, analogous structures include vents in biological organisms, exchange membranes, interfaces where material and energy movement are regulated. The comparison was never spoken explicitly in early meetings. No one wanted to be the first to say it, but everyone was thinking it. Then came the final blow. By running simulations, researchers discovered that the pulses weren't simple heating and cooling, they corresponded to energy consumption. Some hotspots warmed up without receiving external energy, meaning something internal was generating heat. Others cooled rapidly in synchronization with the heating of neighboring nodes, as though energy were being redistributed. Redistribution, coordinated shifts, directed energy flows. This is what living systems do. Cells do it. Ecosystems do it. Brains do it. Rocks do not. The more the team analyzed the thermal behavior, the clearer the picture became. 3I Atlas wasn't behaving like an object. It was behaving like a system. A network with rules. A network with patterns. A network with what Martinez reluctantly described as functional topology. And yet, even as these implications hung heavily in the air, the most troubling realization had not yet been spoken aloud. If the thermal network reflected organized internal processes, what was powering them? What was maintaining them? What was coordinating them? Natural systems don't spontaneously generate this kind of structured behavior. Even early Earth microbes required energy gradients, transport mechanisms, and cellular architecture. Whatever 3 Atlas is, it has those, or something like them. But the most frightening aspect of all? The thermal map didn't just indicate coordinated activity. It indicated change. Over the course of 72 hours, new nodes appeared. Old ones vanished. Connections strengthened or weakened. The network evolved, adapted, reconfigured itself. If the chemistry hinted at lifelike processes, the thermal network removed the hint. It painted the clearest picture yet. Something inside 3I Atlas is active. Something is functioning. Something is responding. And whatever is orchestrating these patterns, it is not behaving like geology. It is behaving like intention. But the next layer of data, the isotopic fingerprint, would push the scientific community past the threshold of doubt into a territory very few were emotionally prepared to accept. If the thermal networks of 3I Atlas made researchers uneasy, the isotopic analysis sent a shockwave through every institution involved. It was the kind of evidence that didn't whisper or imply, it pointed directly, unmistakably, toward one conclusion. A conclusion no scientist wants to reach without overwhelming proof. A conclusion they now had no choice but to face. Because isotopes, unlike heat or molecules, do not lie. They don't fluctuate randomly. They don't organize themselves. They don't just happen to form in the exact patterns associated with biological activity. Isotopes are history etched into matter, the unalterable record of the processes that shaped it. And what 3I Atlas revealed shattered the boundary between speculation and reality. At first, isotopic readings were expected to be routine. Analysts looked for the standard ratios: carbon 1,2 to carbon 1,3, nitrogen 1,4 to nitrogen 1,5, sulfur 3,2 to sulfur 3,4. Every celestial body in the solar system fits predictable profiles shaped by either primordial formation or billions of years of exposure to cosmic radiation. But 3I Atlas didn't match any known profile. Not comets, not asteroids, not interstellar dust clouds, not exoplanet debris, nothing. Instead, the ratios they found looked eerily familiar not to astronomers but to biologists. The carbon isotopes were the first red flag. On Earth, biological systems preferentially incorporate lighter carbon isotopes. Life selects carbon 1,2 because it forms bonds more quickly, enabling faster metabolic reactions. This selective uptake leaves a distinct signature. Biological carbon contains a measurable enrichment of carbon 1,2. 3I Atlas showed the same enrichment, not approximate, not similar, not within the range of possibility, identical. The nitrogen data followed with the same pattern. Nitrogen 1,4 was disproportionately present, exactly the kind of fractionation produced when enzymes cycle nitrogen through metabolic pathways. Even the sulfur isotopes matched the telltale pattern of biological processing. It wasn't one isotope behaving strangely. It was all of them. And the magnitude of the shifts was devastating for any natural explanation. On Earth, these fractionation patterns are the fingerprints of metabolism. Life leaves them behind the way a living organism leaves footprints in sand. If you find them in a rock sample, you know something living influenced its chemistry. And now, that unmistakable pattern was present in an object from deep interstellar space. Some tried to salvage alternative interpretations. Could cosmic rays selectively destroy certain isotopes? Could thermal migration bias one isotope over another? Could we be sampling surface contamination? But every one of those possibilities collapsed under the weight of the data. Cosmic rays don't produce this level of fractionation. Thermal gradients don't create consistency across multiple elements. And contamination would show mixed signals, not the perfectly aligned pattern across the entire object. Still, the most unnerving part wasn't that isotopes aligned with biology. It was that they aligned with active biology. The ratios weren't static. Over the 72-hour observation window, subtle shifts occurred. The abundance of carbon-1,2 increased fractionally as certain spectral lines intensified. Nitrogen-1,4 rose in regions near the thermal hotspots while declining in inactive areas. Sulfur isotopes fluctuated in step with molecular changes. These were not the frozen isotopic signatures of something that once lived. These were the dynamic signatures of something that was living. In biology, isotopic ratios shift as organisms metabolize, process nutrients, and reorganize internal chemistry. The tiny changes observed in 3I8LAS were small, almost imperceptible, but present. And they mirrored exactly the kind of fractional adjustments you'd expect from active chemical cycles. At this point, several scientists refused to continue working alone in their offices. Teams formed spontaneously, huddled in clusters late into the night, staring at screens with expressions suspended between awe and dread. Because with isotopic evidence, speculation was no longer speculation. You cannot fake isotopic fingerprints. Not with random chemistry. Not with exotic minerals. Not with geological anomalies. To produce this pattern, you need one of two things: life, or the deliberate mimicry of life. Either possibility was staggering. Then came the spatial mapping of these isotopes. By aligning isotopic data with Webb's imaging, a disturbing pattern emerged. Areas around the apertures, the same openings linked to thermal activity and complex molecules, showed the strongest biological fractionation. The farther from the apertures, the weaker the pattern became. This was not uniform processing. It was concentrated, localized, targeted. Nature does not target. Life does. With each new dataset, doubt evaporated. Not because scientists suddenly wanted alien biology to be real, but because the evidence made disbelief irrational. Dr. Sarah Hammond at Oxford, known for caution bordering on skepticism, wrote in her internal memo, "If these signatures had come from a rock sample on Earth, we would declare biological activity instantly and without controversy. The fact that they originate from an interstellar object does not invalidate the interpretation. It only makes it unprecedented." Her message circulated through NASA, then through ESA, then through every collaborating institution. No one challenged it. The isotopes told a story older than our solar system, written into matter that had traveled for millions of years through the void, still carrying the unmistakable imprint of metabolism. And yet, as shocking as the isotopic evidence was, it still didn't fully capture the scale of the mystery. Because buried within the spectroscopic noise, researchers found something else. Something far more alien than isotopes or molecules. 17 absorption lines that matched no known compound in any Earth-based database. Not biological signatures as we know them. Not chemical formations we understand. Not molecules that exist anywhere in the natural world. And the moment researchers realized this, a new and far more unsettling question emerged. If these molecules didn't evolve on Earth, could they belong to a form of life that evolved somewhere else? The next section would bring that possibility into focus and push the scientific community across a line they would never be able to uncross. If the thermal networks of 3I8LAS made researchers uneasy, the isotopic analysis sent a shockwave through every institution involved. it was the kind of evidence that didn't whisper or imply, it pointed directly, unmistakably, toward one conclusion. A conclusion no scientist wants to reach without overwhelming proof. A conclusion they now had no choice but to face. Because isotopes, unlike heat or molecules, do not lie. They don't fluctuate randomly. They don't organize themselves. They don't just happen to form in the exact patterns associated with biological activity. Isotopes are history etched into matter, the unalterable record of the processes that shaped it. And what 3I Atlas revealed shattered the boundary between speculation and reality. At first, isotopic readings were expected to be routine. Analysts looked for the standard ratios, carbon 1,2 to carbon 1,3, nitrogen 1,4 to nitrogen 1,5, sulfur 3,2 to sulfur 3,4. Every celestial body in the solar system fits predictable profiles shaped by either primordial formation or billions of years of exposure to cosmic radiation. But 3I Atlas didn't match any known profile. Not comets, not asteroids, not interstellar dust clouds, not exoplanet debris, nothing. Instead, the ratios they found looked eerily familiar not to astronomers but to biologists. The carbon isotopes were the first red flag. On Earth, biological systems preferentially incorporate lighter carbon isotopes. Life selects carbon 1,2 because it forms bonds more quickly, enabling faster metabolic reactions. This selective uptake leaves a distinct signature. Biological carbon contains a measurable enrichment of carbon 1,2. 3I Atlas showed the same enrichment. Not approximate, not similar, not within the range of possibility. Identical. The nitrogen data followed with the same pattern. Nitrogen 1,4 was disproportionately present, exactly the kind of fractionation produced when enzymes cycle nitrogen through metabolic pathways. Even the sulfur isotopes matched the telltale pattern of biological processing. It wasn't one isotope behaving strangely. It was all of them. And the magnitude of the shifts was devastating for any natural explanation. On Earth, these fractionation patterns are the fingerprints of metabolism. Life leaves them behind, the way a living organism leaves footprints in sand. If you find them in a rock sample, you know something living influenced its chemistry. And now that unmistakable pattern was present in an object from deep interstellar space. Some tried to salvage alternative interpretations. Could cosmic rays selectively destroy certain isotopes? Could thermal migration bias one isotope over another? Could we be sampling surface contamination? But every one of those possibilities collapsed under the weight of the data. Cosmic rays don't produce this level of fractionation. Thermal gradients don't create consistency across multiple elements. And contamination would show mixed signals, not the perfectly aligned pattern across the entire object. Still, the most unnerving part wasn't that isotopes aligned with biology. It was that they aligned with active biology. The ratios weren't static. Over the 72-hour observation window, subtle shifts occurred. The abundance of carbon 1,2 increased fractionally as certain spectral lines intensified. Nitrogen 1,4 rose in regions near the thermal hotspots while declining in inactive areas. Sulfur isotopes fluctuated in step with molecular changes. These were not the frozen isotopic signatures of something that once lived. These were the dynamic signatures of something that was living. In biology, isotopic ratios shift as organisms metabolize, process nutrients, and reorganize internal chemistry. The tiny changes observed in 3I Atlas were small, almost imperceptible, but present. And they mirrored exactly the kind of fractional adjustments you'd expect from active chemical cycles. At this point, several scientists refused to continue working alone in their offices. Teams formed spontaneously, huddled in clusters late into the night, staring at screens with expressions suspended between awe and dread. Because with isotopic evidence, speculation was no longer speculation. You cannot fake isotopic fingerprints, not with random chemistry, not with exotic minerals, not with geological anomalies. To produce this pattern, you need one of two things: life or the deliberate mimicry of life. Either possibility was staggering. Then came the spatial mapping of these isotopes. By aligning isotopic data with Webb's imaging, a disturbing pattern emerged. Areas around the apertures, the same openings linked to thermal activity and complex molecules showed the strongest biological fractionation. The farther from the apertures, the weaker the pattern became. This was not uniform processing. It was concentrated, localized, targeted. Nature does not target. Life does. With each new dataset, doubt evaporated. Not because scientists suddenly wanted alien biology to be real, but because the evidence made disbelief irrational. Dr. Sarah Hammond at Oxford, known for caution bordering on skepticism, wrote in her internal memo, "If these signatures had come from a rock sample on Earth, we would declare biological activity instantly and without controversy. The fact that they originate from an interstellar object does not invalidate the interpretation. It only makes it unprecedented." Her message circulated through NASA, then through ESA, then through every collaborating institution. No one challenged it. The isotopes told a story older than our solar system, written into matter that had traveled for millions of years through the void, still carrying the unmistakable imprint of metabolism. And yet, as shocking as the isotopic evidence was, it still didn't fully capture the scale of the mystery. Because buried within the spectroscopic noise, researchers found something else. Something far more alien than isotopes or molecules. 17 absorption lines that matched no known compound in any Earth-based database. Not biological signatures as we know them. Not chemical formations we understand. Not molecules that exist anywhere in the natural world. And the moment researchers realized this, a new and far more unsettling question emerged. If these molecules didn't evolve on Earth, could they belong to a form of life that evolved somewhere else? The next section would bring that possibility into focus and push the scientific community across a line they would never be able to uncross. If the unidentified molecules were the moment scientists realized they were examining something unprecedented, the bioluminescence was the moment they understood it was something alive. Not metaphorically alive. Not active chemistry or complex processes or any of the cautious language researchers had used up to this point. Alive. Because nothing in the universe produces structured light in the dark unless it has a reason to. James Webb's mid-infrared instruments had already shown the heat pulses. The spectrograph had revealed impossible molecules and biological isotopic ratios. But hidden inside the observation streams, faint and almost lost beneath instrumental noise, there was a glow not from thermal radiation, not from reflected sunlight, not from cosmic interactions. A glow that persisted in the darkness. A glow that pulsed. A glow that behaved. At first, analysts dismissed the signal as an artifact, a calibration echo, a software glitch, maybe even stray light bouncing inside Webb's detectors. But when the data was reprocessed independently by multiple teams in different labs using different algorithms, the same result appeared. Discrete photonic emissions coming from multiple regions across 3I Atlas. And not just emissions whose wavelengths were narrow, structured, and consistent with a process no one wanted to admit. Phosphorescence triggered by biochemical excitation. To understand the shock this caused, you must grasp the difference between light reflected by an object and light generated by one. Stars reflect. Ice reflects. Rock reflects. Life glows. Earth's oceans are filled with organisms that illuminate in the dark. Fireflies, jellyfish, coral, plankton. Their light isn't a byproduct. It's communication, camouflage, mating signals, defense mechanisms, biology with purpose. So when Dr. Amanda Foster, one of the world's authorities in bioluminescence, examined the spectral signature from 3I Atlas, she didn't hesitate. She didn't equivocate. She simply said, "This is bioluminescence. Not similar to, not reminiscent of, it is." Her assessment, internal at first, spread like a shockwave. Because the signal was unmistakable. Narrow band emission peaks. Intensity ratios matching oxidation-driven photon release. Decay curves consistent with enzyme-mediated reactions. Repeatable excitation cycles. coherent timing with thermal pulses, variability in rhythm, suggesting regulation rather than randomness. Nothing in geophysics behaves this way. Nothing in astrochemistry behaves this way. Nothing in known physics behaves this way without a biological mechanism. And yet, this wasn't Earth life. The emission wavelengths didn't match luciferin, lophine, bacterial FMN systems, dinoflagellate pathways, or any of the dozens of bioluminescent families known to science. This was an alien system built on molecules we had never seen, using pathways we couldn't map, generating light in ways that defied our understanding. But the shock wasn't just that something was glowing. It was where it was glowing. The bioluminescent signals originated around the same apertures and hotspots where complex molecules, isotopic anomalies, and structural patterns concentrated. These weren't random patches of light. They were active zones, functional zones, places where internal processes were strongest. On Earth, bioluminescence appears in organisms for reasons linked to communication, predation, navigation, mating, and information. So when researchers plotted the pulses over time, an even stranger pattern emerged. The emissions weren't steady. They weren't chaotic. They weren't synchronized with rotation or solar illumination. Instead, they formed sequences, not periodic like a heartbeat, not uniform like oscillations, but deliberate clusters of pulses arranged in patterns that repeated, then changed, then repeated again with variations. Patterns that suggested modulation, patterns that suggested signaling. This is where the tone inside NASA shifted from scientific curiosity to something closer to existential dread. Because the pulsations were coordinated with the thermal network, and the thermal network was coordinated with molecular shifts, and the molecular shifts were coordinated with isotopic changes. In other words, everything heat, chemistry, structure, light was part of the same system. Not random, not geological, not chemical, biological. But even that word began to feel insufficient. Because nothing on Earth uses light this way. Nothing on Earth pulses with chemical, thermal, and photonic coherence across tens or hundreds of meters. Nothing on Earth uses bioluminescence to coordinate macroscopic structures the size of buildings. Whatever is inside 3I Atlas isn't simply life. It may be something beyond life as we define it, a distributed organism, a colony-level intelligence, or a system designed to function as both biology and infrastructure. Some researchers propose that the bioluminescent patterns could be a form of communication within the system, a way for different regions to talk, to synchronize functions, to regulate internal cycles. Others suggested the emissions might serve as a defensive response, an adaptation to deep space radiation, or a metabolic byproduct of chemical processes happening within the apertures. The most daring interpretation, discussed only in private calls and encrypted channels, was that the bioluminescence might not be internal communication at all. It might be external, a signal, a probe, a scanning mechanism, a way of perceiving the outside environment, or worse, a way of announcing presence. At this stage, no one could deny the truth. Something within 3I Atlas wasn't just alive. It was active. It was functioning. It was behaving. Which led to the question no one in the scientific community wanted to ask. If it is communicating, who is it communicating with? And why is it getting closer? The next section would force humanity to confront the final, unavoidable realization. 3I Atlas isn't just alive. It is approaching Earth, and its trajectory no longer appears accidental. For weeks, every startling discovery about 3I Atlas had come from inside the object. Its molecules, its isotopes, its impossible chemistry, its organized thermal web, its alien bioluminescence. But now the focus shifted outward towards something even more frightening in its simplicity, its movement. Because while scientists were busy analyzing the internal mysteries of 3I Atlas, orbital dynamicists at NASA's Jet Propulsion Laboratory were watching something else. Its path through the solar system. And what they discovered was the moment everything changed. At first, 3I Atlas was behaving exactly as expected for an interstellar object. It entered our system on a hyperbolic trajectory, a one-way pass, never to return, just like the few interstellar visitors detected before it. Its speed, angle, and motion were entirely consistent with an object drifting between stars for millions of years. Until it wasn't. Because sometime around perihelion, its closest point to the Sun, 3I Atlas did something no natural object has ever been observed doing. It changed course. Not slightly. Not the minor deviation caused by outgassing or uneven heating. A measurable, deliberate shift. A maneuver. Dr. Lisa Martinez at JPL, the lead on orbital analysis, initially refused to believe it. She reprocessed the data twice. Then again. She recalibrated star field references, corrected for solar wind, radiation pressure, telescope jitter, micrometeorite hits, anything that could produce a false signature. But the result was always the same. 3I Atlas had altered its trajectory with precision. That's when the tone in internal messages took a sharp turn. What began as interesting anomaly quickly evolved into urgent review, then potentially intentional activity, and finally the phrase no one wanted to write. Non-gravitational acceleration, inconsistent with known physical mechanisms. Objects don't change their own orbits. Not comets. Not asteroids. Not interstellar debris. Unless something inside them exerts force. And 3I Atlas had exerted force. The approach toward Earth begins. After the maneuver, 3I Atlas settled into an elliptical orbit, not an escape path, not a dying slingshot around the Sun, but a stable orbit that kept it bound to our star. For the first time in recorded history, an interstellar object wasn't leaving us. It was staying. And its new orbit carried an even more unsettling implication. It was spiraling inward, toward the inner solar system, toward the region of Earth's orbit. The numbers weren't ambiguous, not after repeated verifications, not after refinements using updated telemetry. The object's path would bring it frighteningly close to Earth, within 0.08 astronomical units. That's about 30 times the distance to the Moon in cosmic terms. In astronomical terms, it's practically a handshake. Then came the calculation that sent a ripple of unease through every agency involved. Time until closest approach, 47 days. 47 days until the biological, chemical, and thermal anomaly was close enough to observe in high detail. 47 days until we might detect external signals. 47 days until we might receive something, or be seen, or be evaluated, or be engaged. The velocity problem. As troubling as the trajectory was, the velocity raised even more questions. 3I Atlas was not approaching at runaway interstellar speeds. It had slowed far more than expected from gravity alone. At closest approach, it would be moving at roughly 22 kilometers per second relative to Earth. That's fast for human spacecraft. But for an interstellar object that entered the solar system at 4 times that velocity, it was shockingly slow. Almost controlled. Almost like it was pacing itself. Almost like it was managing the timing of its approach. The impossible coincidence. When the orbital data was finalized, Marcella Hayden at ESA's NEO Coordination Center wrote the line that appeared in every internal summary afterward. If this approach were random, it would be the most improbable coincidence in the history of celestial mechanics. Because the object wasn't just passing near Earth. It was entering a trajectory that provided a clear, unobstructed line of observation of our planet, ideal for imaging, ideal for sensing, ideal for scanning, ideal for making decisions. As one JPL analyst put it bluntly in a private message, it's not flying by, it's positioning. The elephant in the room, intent. By this point, refusal to consider intention was no longer intellectual rigor. It was denial. Every natural explanation had been exhausted. Asymmetrical outgassing, impossible, there were no jets. Yarkovsky effect, too weak by orders of magnitude. Solar radiation pressure, directionally wrong. Tidal forces, negligible. Magnetic interactions, not strong enough. The movement required directed force. Directed force required a mechanism. A mechanism required systems. And systems required something else: purpose. But purpose is a word that scientists wield with caution bordering on fear, because purpose implies agency, and agency implies intelligence, and intelligence implies something no one was ready to accept. We are not alone, and whatever is inside 3I Atlas is making decisions. The internal speculation fractured into 3 interpretations. 1. Curiosity, a probe approaching for observation, mapping, and study drawn by Earth's biosignatures. 2. Indifference, a system following pre-programmed instructions or biological imperatives, unaware or unconcerned about humanity. 3. Evaluation, a system adjusting its approach based on what it detects, assessing Earth, our signals, our activity. The scientists didn't say the 4th interpretation aloud. Not yet. But everyone felt it. If an object with internal biological systems, complex molecules, thermal communication networks, phosphorescent signaling, engineered compounds, were deliberately approaching Earth, then this might not be an accident. It might be contact, or something that comes before contact. And with only 47 days remaining, the time for speculation was rapidly shrinking, because the final piece of data, the one no one wanted, was about to reveal exactly how much control 3I Atlas had over its movement, and whether it was moving of its own free will. By the time all the data was laid out, the biological signatures, the thermal networks, the engineered molecules, the bioluminescent pulses, the maneuvering trajectory, the scientific community had reached a moment it had spent decades imagining, yet hoped would never arrive. A moment when the universe stops being a distant, indifferent backdrop and becomes a participant. Something inside 3I Atlas was active. Something was functioning. Something was approaching Earth on a trajectory too precise, too controlled, too intentional to dismiss as chance. Now came the question that no one in academia, government, or defense wanted to confront. What does it want? And more importantly, what does it mean for us? Because buried beneath every analysis, every meeting, every memo filled with cautious scientific language, there was a quiet, escalating fear. We are no longer observers, we are being observed. 1. The optimistic interpretation, curiosity. The most hopeful scenario, the one many scientists clung to out of rational optimism, was simple. 3I Atlas is a probe, a scout, a biological or biomechanical vessel sent by an advanced civilization to study star systems. Earth, with its oxygen-rich atmosphere and biosphere, would naturally attract interest. We have been broadcasting radio waves for a century. Our planet glows with industrial signatures detectable from dozens of light years away. To an advanced intelligence, we would be obvious and, perhaps, interesting. Under this interpretation, 3I Atlas was never hostile. Its biological systems weren't weapons or mechanisms of conquest. They were sensors, processors, self-repairing materials, distributed networks designed for resilience and longevity. A living probe, an autonomous explorer, a biological spacecraft. Something sent to learn, not to harm. If this version is correct, then the close approach could be humanity's greatest opportunity. First contact with an intelligent species that mastered biotechnology on a scale we can barely comprehend. But even the optimists admitted one problem. Curiosity does not require trajectory maneuvers. It does not require bioluminescent signaling. It does not require this level of complexity. It does not require getting this close. This is the optimistic scenario, but not the most likely. 2. The neutral interpretation, indifference. In this scenario, 3I Atlas isn't reacting to us at all. It isn't deciding anything. Instead, we are witnessing an automated process, and a program set millions of years ago, a biological machine running predetermined behaviors, a system incapable of caring whether Earth has life or not. It could be a seed pod, a drifting colony organism, a dormant ark, or the relic of a long-gone civilization whose technology continues functioning by inertia alone? If so, this approach might not be about Earth at all. It might simply be following a biological imperative, like a spore drifting toward warmth, or a microbial colony expanding toward resources. Indifference could be safer than hostility, but it is not necessarily safer than intention, because something indifferent to us might still be dangerous by accident, like walking into the path of a machine that doesn't know you exist, like touching an organism that does not distinguish you from environment. And if 3I Atlas is indifferent, then we are irrelevant. And irrelevant things can be consumed, overwhelmed, or destroyed without malice. This is the scenario scientists discussed in hushed tones when they allowed themselves to be honest. 3. The scenario everyone fears: evaluation. This is the interpretation no one wanted to articulate, but which the data quietly, steadily pointed toward. A system that detects complex biological molecules, regulates heat, distributes information, communicates through photonic pulses, alters trajectory, slows to approach as, positions itself for optimal observation, is not merely alive, it is aware. Not aware in a human way, not necessarily conscious, but aware enough to sense, react, and adjust. Under this scenario, 3I Atlas might not be a probe. It might be something more ancient and fundamental: a cosmic surveyor, a biological sentinel, an automated arc, or a sophisticated organism designed to perform long-duration reconnaissance across star systems. An evaluator, something that classifies worlds, something that identifies biospheres, something that approaches to assess them. If this interpretation is true, the approach is not random. It's not a coincidence. It's not a malfunction. It is a choice, and choices imply criteria, which raises a question more disturbing than any other. What happens after evaluation? The possibilities range from benign to catastrophic: peaceful contact, data collection, environmental sampling, harmless observation, technological exchange. But the same mechanism might also judge Earth as a potential threat, evaluate humanity's stability, determine habitability for colonization, search for resources, decide whether our planet meets unknown criteria for survival. Or worse, we might be a data point in a process older, colder, and larger than ourselves. An assessment mechanism we don't understand, built by a species whose values and logic may be incomprehensible. 4. The scenario no one wants to name. There is one final possibility, the one scientists avoid even in private calls, because acknowledging it crosses into the realm of existential alarm. Predation, acquisition, harvesting, not necessarily malicious, just biological. In ecosystems, complex organisms consume simpler ones. Colonies spread. Symbiotic systems absorb new hosts. Parasitic systems infiltrate. Life expands where it can. If 3I Atlas is biological, if it requires resources, if it has needs, then Earth, with its atmosphere, oceans, complex chemicals, and organic abundance, is a feast. No one claims this openly, but no one can rule it out. The uncomfortable truth. The scientists, the governments, the agencies, all of them now face one central truth. Whatever is inside 3I Atlas is not just alive, it is active. It is intelligent in some form, and it is coming closer. Close enough to observe us in detail, close enough to interact, close enough to act on whatever purpose brought it here. And the margin for preparation, the time humanity has to understand this thing, interpret its intentions, and decide how to respond, is shrinking fast. Because an object with biological networks, unknown molecules, a living interior, and controlled trajectory will reach near-Earth space in 47 days. The final section will confront the reality that can no longer be avoided. Humanity is about to face the most consequential moment in its history, and we may not be ready. For centuries, humanity looked up at the night sky and asked the same question in 1,000 different ways. Are we alone? It was a question whispered around campfires, written in ancient myths, pursued through telescopes, encoded in radio transmissions, and embedded in every scientific mission seeking other worlds. But it was always a distant question, philosophical, theoretical, comfortably abstract. 3. iAtlas has ended that era. Because the data now paints a picture so coherent, so overwhelming, so profoundly transformative that denying it would no longer be caution, it would be delusion. Inside that object, the same object that crossed interstellar space, maneuvered inside our solar system, altered its trajectory deliberately, and is now closing in on Earth, exists something organized, something structured, something biochemical, something active, something alive. Not life as we know it, not carbon-based cells, not microbial fossils frozen in crystal lattices, something that builds molecules we cannot identify, something that distributes heat in patterns too intelligent to be random, something that ignites its own light in the dark vacuum of space, something that displays metabolic isotopic signatures, something that monitors its environment, something that adapts, and now something that approaches. The implications reverberate far beyond astronomy. This discovery fractures the walls between disciplines, dissolves the boundary between science and philosophy, and forces humanity to confront its position in a universe that suddenly feels smaller, more crowded, more alive. We do not know if iAtlas is a probe, a vessel, an organism, a colony, or something that transcends our categories. We do not know whether its approach represents curiosity, indifference, evaluation, or intent. We do not know whether it is automated or conscious, ancient or new, exploratory or predatory. But we do know this: in 47 days, it will be close enough for the truth to reveal itself. And that countdown is no longer theoretical. It is happening now. Governments are meeting behind closed doors. Space agencies are coordinating telescopes across the planet. Spectrographs, radar arrays, wide-field sensors, and communication systems are already pointed toward a tiny, dark object drifting through space. An object whose interior pulses with heat, reacts with chemistry, and glows as though speaking in a language we do not yet understand. Nations are preparing contingency plans. Scientists are preparing announcements. And humanity, knowingly or not, stands on the threshold of the most consequential moment in its existence. Every civilization in history has dreamed of first contact, of the moment when we learn we are not the sole spark of consciousness in the universe, but no civilization has ever been prepared for it. We are no exception. We do not know whether this encounter will bring knowledge or danger, wonder or fear, transformation or destruction. We do not know whether we will be greeted, ignored, studied, or judged. But what we are discovering as iAtlas drifts toward our world, alive with impossible chemistry, is that the universe does not wait for us to be ready. It simply arrives. And now, with the James Webb Space Telescope's revelations echoing across the scientific world, humanity must face a truth we spent generations imagining and avoiding in equal measure. We are not alone. And whatever has noticed us is almost here. In the coming weeks, we will observe more. We will listen harder. We will prepare for everything yet understand almost nothing. Because this moment belongs not to fear or speculation, but to awareness. The universe has finally answered us. The question now, the one whose answer will define our species, is no longer, are we alone? It is, what happens next?